Welcome to the ICE tables video. By the end of this video, you should understand when using an ICE table is appropriate and understand how to perform equilibrium calculations using an ICE table. So what is an ICE table? It's an acronym. The I stands for initial concentrations, or in some cases partial pressures, depending on what phase your reactants and products are in. C stands for change, and E stands for equilibrium concentrations, or again, partial pressures if you're dealing with gases. These can be used to calculate a K value when given initial conditions and a change, or to calculate equilibrium concentrations when given a K value and initial concentrations. I'll show you examples of each. Here are the general steps for using an ICE table. First, you want to make sure to write out the K expression. This is a step that people often want to skip, but it's actually really crucial to prevent you from making needless errors. Then you set up the ICE table, which I'll show you in the next slide, fill in what you know, and use stoichiometry to fill in the rest. So let's put these steps into practice. Here's an example where we're asked to solve for K given concentrations. A solution initially contains 0.55 molar A and B. The following balanced equation occurs, and the equilibrium concentrations for B is found to be 0.21 molar. What is the K for this reaction? So as we saw in our steps, I'm going to start by writing out the K expression for this reaction. In this case, we're going to do C squared, because it's our reactant, over the concentration of A times the concentration of B, both raised to the first power. Now I'm going to fill in what we know in our ICE table. We know that initially we had 0.55 molar A and 0.55 molar B. We can assume that we have no C to start, since we're not told that there's any C in the system. And then we're told that at equilibrium, we have 0.21 molar B. Based on this information, we can now fill in the things we don't know. So since we're given the initial B and the equilibrium B, we can find the difference. Subtracting, we find that B has decreased by 0.34 molar. Notice that both A and B are in a 1-to-1 ratio to one another. That means if B went down by 0.34 molar, A also went down by 0.34 molar. What does that tell us about C? Well, if our reactant concentrations are decreasing, that means our product concentrations must be increasing. Stoichiometrically, we see that we have a 1-to-2 ratio of reactants to products. So if A and B each went down by 0.34, then C must have gone up by 0.68, which is double 0.34. From here, I can do the math and find the equilibrium concentrations of the two things that I was missing. And then I can plug them into my K expression. So 0.68 squared over 0.21 times 0.21. And that gives us a K value of 10.5. Remember, the K values are unitless. Now let's try solving for concentrations using the K value. This is a little bit trickier. So I'm going to start once again by writing out my K expression. Notice it's the same equation, so it's going to be the concentration of C squared over the concentration of A times the concentration of B. And in this case, we're actually given the K value, so I'm going to go ahead and put that in here so that we can keep track. Now we can fill in what we know on our ICE table. So we know the initial concentrations of A and B, and we also know that C begins as 0. Now this case is a little trickier because we don't know the change. We're not given any information about equilibrium concentration, so we can't calculate a change. However, we do know that since there's no C present, the reaction must proceed in the forward direction, meaning we must be using up A and B and creating C. We also know the ratio in which that's happening. So I'm going to call our change X. So A is going to go down by X, and because A and B are in a 1-to-1 ratio to each other, B will also go down by X. And since C is in a 2-to-1 ratio with A and B, C will go up by 2X. From here, I can do my math, and you'll see that you're left with some complex math to do here. So let's go ahead and plug this into the equation. We know that 2 times 10 to the negative third will be equal to 2x squared. Be careful to square that whole term, not just the x. Divided by 1.25, minus x times 1.25 minus x, which I'm just going to call 1.25 minus x squared. This looks complicated to solve, but you'll notice that I can actually just take the square root of both sides here. So taking the square root of the k value, I get 0.045. And then since I'm taking the square root of two things that are each squared, that will be 2x over 1.25 minus x. From here, it's just some algebraic manipulation, which I'm not going to show all of. And so doing this algebra, you should get x equals 0.028. Now be careful, that's not your final answer, right? We were asked for equilibrium concentrations. So we have to go back to our initial equation. The concentration of A, as we said, is going to be 0.125 minus x. We just determined what x is, so that actually means it's going to be 1.25 minus 0.028, which is 1.22 molar. So that's our concentration for both A and B, since they were the same expression. Our concentration of C then is going to be 2x, which is actually just 2 times 0.028, and that gives us 0.056 molar for C. Here's two examples to try on your own. Pause the video here and try each of these examples. There's one of each of the two types that we reviewed in this video. Also be mindful of the fact that in this case, I've given you moles and liters, not molarity. So you'll have to do some initial molarity calculations to get this started. When you come back, I'll reveal the answers. Welcome back. Here's what you should have gotten for number 1. In this case, we were given initial and equilibrium conditions, so I was able to calculate a change. I took into account the stoichiometry, being 2 to 1 to 4, and I was able to, and that allowed me to calculate equilibrium concentrations and then a K value. Here's what you should have gotten for number 2. This example was one where you were not given the equilibrium concentrations, so you didn't know the change, so you had to use X for the change, therefore giving you this somewhat complicated mathematical expression, simplifying for X, and then coming over here and actually using that X value to calculate the concentrations at equilibrium. Before we end, just a few tips and tricks to help you avoid common errors. There's a lot of steps in these problems, and there's a lot of places where people make really common errors. So here's some things to make sure that you do to avoid those. First, don't forget to consider the stoichiometry. You have to consider the ratio in which things are reacting. In this case, we had a 2 to 1 to 1 ratio. Therefore, if H2 is going up by X, HI must be going down by 2X. Also, don't forget that X isn't always your answer. As we saw in the previous example, we had to go back and actually plug X into the expressions to solve for the concentrations, which is what the question asked for. And finally, always write out the K expression before you begin plugging values into it. I know it's tedious and it's often a step people want to skip, but when you skip that step, it's easy to forget about things like the exponents in the expression. That brings us to the end of this video. Let's review our goals. First, we looked at when to use an ICE table, and then we looked at how to perform calculations using an ICE table.